Today's tape is to explain biaxial crystal optics. Now, in order to understand what biaxial crystals are, we have to talk about optic axes in general. An optic axis is a direction in which both plane polarized components travel the same velocity. In uniaxial crystals, there is only one direction in which both plane polarized components travel the same velocity. Uniaxial, one optic axis, and that optic axis is tied to the C crystallographic axis. Biaxial crystals make up a second class because in biaxial crystals there are two optic axes. So the distinction between uniaxial and biaxial then comes in the number of directions in which both plane polarized components can travel the same velocity. Now, in order to describe biaxial crystals and their relief, we have to use a different convention than we have used for uniaxial minerals. And so there are now three refractive indices. And these, by convention, are called alpha, beta, and gamma. Again, unlike the uniaxial minerals, we have a very strict convention about alpha, beta, and gamma. It works in such a way that the alpha is always the lowest of the three refractive indices. Beta is always the intermediate refractive index, and gamma is always the highest refractive index. Now, there is also a convention about nomenclature with regard to the vibration directions within biaxial minerals. And we talk about three individual vibration directions, X, Y, and Z. And these vibration directions are directly associated with the alpha, beta, and gamma refractive index. That is, the X-ray of biaxial minerals has the refractive index alpha. It is always, because it's always the lowest refractive index, X is always the fast vibration direction. And conversely, Z is always the slowest of the three vibration directions, and it has the refractive index gamma. The intermediate vibration direction we call Y. Its refractive index is beta. Okay, there is a sign convention, an optic sign convention, similar to the optic sign convention that we have for uniaxial minerals. And the optic sign is defined in this way. Minerals are said to be positive if the difference between alpha and beta is small compared to the difference between beta and gamma. That is, the sign depends on the relative spacing of these three refractive index. If beta is closer to alpha than to gamma, then the mineral by definition is positive. If the beta index is closer to gamma than it is to alpha, then the mineral is defined as having a negative optic sign. This is the sign convention then for biaxial minerals. Now, in order to understand the relationships of X, Y, and Z and alpha, beta, and gamma in biaxial minerals, we need to rely on a three-dimensional visualization. And the three-dimensional visualization that we use for this is a device called the indicatrix. Remember, we had an indicatrix for uniaxial minerals. This is the biaxial indicatrix, and it's a more complex kind of body. It's more complex in the following way. It is a triaxial ellipsoid, and it is defined actually by 3 radii. One of the radii is beta, for the beta refractive index. One of the radii is gamma, for the gamma refractive index. And the third radii is alpha, for the alpha refractive index. So you can see if I turn this body in different directions, we have alpha defining this radius, beta defining this radius, and then if we turn the body in a different direction, we can see that the longest radius, because it's the largest refractive index, corresponds to the gamma. So gamma, the highest refractive index, is defined along one axis. Beta, the intermediate, defined along another axis. And alpha, the lowest index, defined along a third axis. So these 3 refractive indices are constructed in such a way that they're all perpendicular to each other, and that's because in the biaxial mineral, the X vibration direction, which has the alpha refractive index, is a vibration direction which is perpendicular to the Z vibration direction, and the X refractive index is also perpendicular to the Y vibration direction. The alpha, here's the alpha refractive index, the X vibration direction, perpendicular to the Y vibration direction, which is constructed here by the beta refractive index. So this is a 3-dimensional body. Now, as you can see on one of the planes that is cut through this indicatrix, I have some dotted lines indicated. These dotted lines are the optic axes of the mineral. They are the directions at which light, the 2-plane polarized components traveling in this direction, will be traveling at the same speed. We'll see why that is true in a minute. But the reason we use this device then is as a visualization to allow us to understand the orientation of some particular mineral grain. And every mineral grain that we observe on the microscope stage has some randomized orientation with regard to the indicatrix. And if we can imagine the indicatrix, even though we never see it, it helps us understand the possible orientations of X, Y, and Z, and therefore helps us understand whether we can measure X, Z, Y independently, therefore determine their refractive indices, alpha, beta, and gamma, independently. Now, one thing I want to do is to show you that there is a special orientation of the indicatrix, which I can look at, which is, in fact, gives me a circular section. Now, the circular section of the indicatrix can be obtained if I turn it a certain way, then the outline of the indicatrix gives me a circle. And this is approximately the orientation here. And what I want you to see is that when I get a circular section, the radius of that circle is, in fact, the beta index. And I've turned the thing at an angle so that the distance from this edge of the indicatrix to this edge is exactly twice the beta index. We have now a circular section of the indicatrix. This is the case when we are looking along an optic axis of this particular indicatrix. Well, in order to visualize this more easily now, I'm going to get away from the 3-dimensional body and use some 2-dimensional diagrams. Okay? Now, the first one, and this involves some nomenclature too, the first section that I'm going to take through this indicatrix is something I'll call the XY plane. And the reason I call it the XY plane is because the Y vibration direction and the X vibration direction are both in this plane. Okay, the one vibration direction is located here, Y, and the other one here, and these two vibration directions then form a plane, which we call the XY plane. Now, the important thing about this particular plane is that the Z vibration direction is perpendicular to it. And the Z vibration direction is oriented just like this in this particular orientation. So if you look at a mineral grain that has this orientation, then it's possible to see the Y vibration direction, which has the beta refractive index, and the X vibration direction, which has the alpha refractive index. But it's not possible to observe the Z vibration direction. And so this is then what we call the horizontal plane of the indicatrix, or the XY plane, where we can observe alpha and beta refractive index and isolate the X and the Y vibration direction. Now there are two other special orientations of the indicatrix that we should worry about. The next one is called the YZ plane. And the difference here now is, this is in a way we can call the side vertical section of the indicatrix. Difference here now is that the X vibration direction is perpendicular. It has this orientation. In every biaxial mineral, the three vibration directions are mutually perpendicular to each other. So X is perpendicular, and now we have the Y vibration direction oriented here, the Z vibration direction here, and we can measure the gamma and the beta refractive indices. Okay, these special kinds of planes, like the XY plane and the YZ plane, we call symmetry planes. The reason we call them symmetry planes is that they represent special orientations of the indicatrix which are exactly symmetrical. Here, for example, is our XY plane on the three-dimensional indicatrix. And if I take this plane and turn it over so that it's oriented perpendicular to you, you can see that it's exactly symmetrical. This half of the indicatrix is exactly the same as this half of the indicatrix. So this is a symmetry plane of the biaxial indicatrix. And there are three symmetry planes. They are all mutually perpendicular. One is this XY plane, oriented here. Another is the YZ plane, oriented in this fashion. And the third symmetry plane is the XZ plane, which has this orientation. And it's the XZ plane which contains the optic axes. So it sometimes is called the optic plane of the biaxial mineral. Now, in thinking about the XZ plane, this special optic plane orientation is an important one when we talk about the distinction of sign of biaxial minerals. So let's look at a detail now of the XZ plane, and I want to show you some geometric constraints. We'll look at the XZ plane first in a positive biaxial mineral. Here is the X vibration direction. Here is the Z vibration direction. Remember that the Y vibration direction is perpendicular to both these planes and is coming outside. But since gamma is the highest refractive index, alpha is the lowest, then it's possible to draw a line within this plane on the center to the edge of the indicatrix, which is exactly equal to the refractive index beta. Now in this particular case we have a positive mineral, and the sign convention tells us then that beta is much closer to alpha than it is to gamma. This means that the trace of this beta line intersection with the edge of the indicatrix is very close to alpha, makes only a very small angle with alpha. Now the optic axis of this, that is one of the optic axes of this particular biaxial mineral, is exactly perpendicular to the trace of beta on this. So I've put in the trace of the optic axis located here. And I think you can see very, very easily that it's possible to draw another line just on the other side of the construction, which will also define beta. And there is also a perpendicular to that line which defines the second optic axis in this biaxial positive mineral. So the optic axes intersect in the same plane as the XZ plane. This is the optic plane then of a positive mineral. Well, let's look at a negative mineral and see how it looks different in this orientation. Here's the case of a biaxial negative mineral now. And again, you see our X vibration direction oriented here. Our Z vibration direction is perpendicular to it. This time, beta, because it's closer to gamma now, by definition in this negative mineral, is measured on the indicatrix here, very close to the gamma direction. And the optic axis is shifted way over into this orientation. The second optic axis then would be defined as the perpendicular to the second trace of beta. Here's the other beta trace in here, and the second optic axis would be found over here on the other side of the figure. So there are always two optic axes, and it is the relationship of gamma, beta, and alpha which determine the position of the optic axes, and they have really a rigid geometric constraint once the alpha, beta, and gamma indices are defined. Well, let's look at the optic plane now of a positive uniaxial mineral again here. Here is the construction with the Z vibration direction. Again, we put conventionally in a north-south position on this plane. The X vibration direction located here. Alpha measured along this axis. Gamma measured along this axis. And the two dashed lines here now correspond to the circular sections of the indicatrix. Those circular sections are located here perpendicular to the edge here, and this distance from the center to the edge is defined by the beta refractive index. And the optic axes are perpendicular to those planes. Here's one optic axis here, another optic axis located here. In this particular construction now, this is a positive mineral, so beta is closer to alpha than it is to gamma. And the optic axes have an acute angle relationship, which is bisected by the Z vibration direction in this particular case. Here's a definition then. We'll define something about the angle between the optic axes, because this angle varies. And we call this angle the optic angle. Now the optic angle is bisected by the Z vibration direction if the mineral is positive. The acute angle between the optic axes is sometimes called 2V. In fact, this is the shorthand notation, 2V. 1V would be simply the angle between the Z vibration direction and one of the optic axes. 2V is twice that 1V angle, and it is defined as the acute angle between the optic axes. And if the mineral is positive, then the vibration direction which bisects the 2V angle is the Z vibration direction. Okay? This is the 2V angle in a positive biaxial mineral. Well, what happens if the mineral is negative? Then the optic plane shifts, and our orientation is like this, and the optic axes now are located down here in this position. The 2V angle is measured, in this case, around X. This is a negative biaxial mineral. The acute angle between the optic axes is bisected now by the X vibration direction. Remember, in the negative mineral now, beta is closer to gamma than it is to alpha. Okay. Well, there is a rigid geometrical constraint which is indicated the minute that alpha and beta and gamma are defined, then the 2V angle is defined as well. And this equation shows the geometrical constraint of the 2V angle. The cosine of V, which is of course half of the 2V angle, is equal to the square root of gamma squared, this is the gamma refractive index, times beta squared minus alpha squared, divided by beta squared times gamma squared minus alpha squared. Okay, this is the geometric constraint. So the minute that I tell you the gamma, beta, and alpha indices of a mineral, you can immediately sit down and calculate its 2V angle by using this particular kind of equation. Well, the 2V angle can be measured only with some difficulty physically with a microscope. And the reason for this is because there is a distortion of the 2V angle that occurs at the interface between a particular mineral and the material surrounding it. Remember that these, if this is air or this is your immersion oil, that there is a difference of refractive index that occurs between the mineral and the material surrounding it. And this makes the 2V angle usually appear to be larger than it actually is. And the difference then between 2V as it actually occurs and 2E, which is something we actually observe, depends on the difference in refractive index between the material surrounding and the mineral grain itself. This means that you can't directly measure 2V and 2V angles by simply manipulating the particular crystal unless you make corrections for the refractory effects that are occurring at the margins of the grain. So we can again do this kind of correction mathematically. Well, let me go through then some simple definitions about the indicatrix. We have something, a symmetry plane of the indicatrix, which is called the optic plane. The optic plane of the indicatrix is that symmetry plane which contains the two optic axes and the x and z vibration directions. The optic plane then is a very special symmetry plane of the biaxial indicatrix. Now there is also a vibration direction which we call the optic normal vibration direction. The optic normal is in biaxial minerals is always the y vibration direction, because y is always the vibration direction that is perpendicular to the optic plane, or the plane that contains the two optic axes. There is another geometric thing to define, the optic angle. The optic angle is the angle between the two optic axes. And this is sometimes also called the 2V angle, because we like to refer to this in a shorthand way. We also use a terminology regarding the angle between the optic axes. We use the terminology BXA, which refers to acute bisectrix. The acute bisectrix then corresponds to the vibration direction, either x or z, which bisects the optic angle, the acute angle between the optic axes. BXA is the vibration direction, either x or z, which bisects the acute angle between the optic axes. Now, we have two possibilities in biaxial minerals. If the mineral is positive, then Z is equal to the BXA. The Z vibration direction is equal to the BXA. If the mineral is negative, then X equals the BXA. And these two things really should be memorized, because you get into a situation where you always need to recall the relationship between optic sign and the BXA of the indicatrix. Now there is another shorthand which we use, which is called BXO. The BXO refers to the obtuse bisectrix. If there is an acute angle between the optic axes in the optic plane, then there also is an obtuse angle. And this obtuse angle then is bisected by the other vibration direction, either X or Z, within the optic plane. So BXA refers to the acute angle, BXO, the obtuse angle between the optic axes. Okay, in summary, symmetry planes of the biaxial indicatrix. There are 3 of these symmetry planes, and they are defined by the possible combinations of vibration directions. One is called the XY plane, and in that particular plane, the Z vibration direction is perpendicular. The X and Y are parallel to that plane. There is the YZ plane, where again Y and Z are parallel and X is perpendicular. And there is the XZ plane, which is a special one, which we also call the optic plane, because besides having the Z and X plane parallel, also both optic axes are parallel. There is also one other special orientation of the indicatrix which is important, and this is something we call the optic axis section. This is the section of when one of the 2 optic axes is exactly perpendicular to the microscope stage. When this happens, then the optic axis is coming out this way, and what we see effectively is a perfect circular section of the indicatrix. And this circle is defined simply by the beta refractive index. So that when the mineral is oriented in this direction, you can see the Y vibration direction. You can measure the beta refractive index. Okay, what about the orientation now of these vibration directions with respect to the crystallographic axes of minerals? Now, this orientation of the X, Y, and Z vibration directions with the crystallographic axis is called, by convention, optic orientation. The relationship between X, Y, and Z vibration directions and the A, B, and C crystallographic axes. This depends on the symmetry of the biaxial minerals. And we have 3 crystal classes which make up the biaxial mineral groups: orthorhombic, monoclinic, and triclinic. And of course, they have different relationships between the lengths and geometric angles between the crystallographic axes. So we'll talk about some possibilities for orientation. For example, we could have the case of where X equals B, Y equals C, and Z equals A. There also are many other combinations and possibilities, but the essential thing is that if the mineral is orthorhombic, the orientation of barite in terms of its crystallographic directions, we also know its optic orientation. Here, for example, is a barite crystal expression of the crystal. This is the side pinacoid, basal pinacoid, side pinacoid, and the mineral is lying on a front pinacoidal section. This means that the A crystallographic axis is coming directly out toward us. This way, the C crystallographic axis is oriented in this vertical direction, in this particular kind of orientation. Now, since barite is orthorhombic, there is a relationship between the A, B, and C axes and the vibration directions. And so for this particular mineral, Y equals B. This means that the Y vibration direction is exactly parallel to the B crystallographic axes and is found in the mineral exactly in this orientation. The C crystallographic axis is tied rigidly to the vibration direction X and is found here in this orientation. And the Z vibration direction is found right here, tied rigidly to the A crystallographic axes. Now, another thing we can see here, I've drawn these in schematically, is the points of emergence of the optic axes. The optic plane across this particular mineral, and this plane contains the optic axis. And one optic axis has this orientation, the other optic axis has this orientation. The angle between them is 37 degrees. So one is tilted in this direction, and the other is tilted somewhat in this direction, and the optic plane of barite is located just like this. Now, some important things occur from this. One is that since these vibration directions are mutually perpendicular in this kind of fashion, if barite is oriented in this way, then extinction occurs at parallel positions. When you look at this barite crystal in cross-polarized light, extinction will occur when these vibration directions coincide with the polarizer and analyzer of the microscope. And that will be when the form of the crystal and the cleavage traces are parallel to the polarizers as well. So barite shows parallel extinction in this kind of orientation. Well, let's look at the mineral in another orientation. This is now in the basal pinacoidal orientation. And here's the barite crystal. Again, we see the side pinacoidal trace coming up this way. The basal pinacoid is now located down here. The basal pinacoid is lying on the stage of the microscope. The front pinacoid is located right in here. Now, in this particular case, the cleavage of barite, which we can see, is the prismatic cleavage. So these prismatic cleavage traces are, of course, going along the C-axis direction, parallel to the C-axis direction, and they have a symmetrical relationship to extinction. Here's the A crystallographic axis, which correlates with Z in barite, the B crystallographic axis, which correlates with Y, vibration direction in barite. The X vibration direction, which correlates with C, is located, of course, in this third kind of plane, and the pinacoidal cleavages show up here. Extinction will be symmetrical in this orientation of barite. And finally, let's look at the third simple kind of orientation of the barite mineral grain, which is shown here. And this now is the side pinacoid plane. That is, the side pinacoid is now parallel to the microscope stage. The basal pinacoid has this plane, located right here. The front pinacoid is now located here. Here is our A crystallographic axis, which correlates with the Z vibration direction. The C crystallographic axis, which correlates with X in this sort of fashion. Remember now, this is the XZ plane of the indicatrix, the optic plane, so it also contains the optic axes. Here's one optic axis here, another optic axis here, and of course the angle between these two optic axes in barite is 37 degrees. Since the mineral is positive, Z is the BXA direction, the acute bisectrix, and Z is located here. And again, our cleavage traces, which include the basal cleavage of barite, which has this orientation, and the prismatic cleavage traces here now occur in a parallel relationship to the vibration directions and, of course, the crystallographic axes of the mineral barite. So this is just one illustration of one kind of orthorhombic mineral and the optic orientation which it exhibits. There are other kinds of relationships when there is a different pairing between X, Y, and Z. When there may be different kinds of cleavage exhibited in the mineral, then there may be different relationships in different orientations. And it's those cleavage relationships, the form relationships, the extinction relationships, and the kinds of correlations with X, Y, and Z and A, B, and C crystallographic axes that give you lots of information to describe the particular mineral and then subsequently to identify it. Now, what if the biaxial mineral that you're looking at is not orthorhombic? What if it's monoclinic or triclinic? And this shows the relationships now between X, Y, and Z and the A, B, and C crystallographic axes in monoclinic and triclinic cases. Remember, monoclinic crystals, the A, B, and C axes are not perpendicular to each other. And yet, X, Y, and Z in all biaxial minerals are always perpendicular. So in either monoclinic or triclinic minerals, it's impossible to have a perfect relationships of X, Y, and Z with A, B, and C axes. In the monoclinic case, there is only one association which occurs, and that is that one of the vibration directions, X, Y, or Z, it can be any of these three, must correlate with the B crystallographic axis. And that is the only geometric constraint that we have in optic orientation with monoclinic minerals. The other crystallographic axes, the A and the C axis, bear some angular relationship with the three vibration directions. And in triclinic mineral, there is no correlation at all except by chance between X, Y, and Z and the A, B, and C axes.